Hi, today we are going to be talking a little bit about molecular geometry. Now, at this point, you guys should be able to figure out what exactly the Lewis structure is of a compound. For example, if I give you CH4, at this point you should be able to draw the Lewis structure and have it look something like that, with the lines being connected and so forth. Now, this is a two-dimensional representation of what is actually a three-dimensional object. If you notice, the angles between these appear to be right angles, okay? However, this is not an accurate representation of what this molecule actually looks like, or the angles between the bonds are not exactly like that. So today we are going to be looking at the different types of simple molecular structures and how we can determine what the molecular structure is. Now, the first one I want to talk to you guys about is a bent structure, okay? Now, bent structures, the atoms are at an angle. For example, a water molecule. Water molecules, right, looking like this and like what you see on the screen, water molecules have about a 105-degree angle between them, and they're made up of only three atoms, a central one and the two ones sticking off from it. The next one is a linear one. Now these are made up of at least three atoms, but here they are all in a straight line, okay? Like this atom, like this molecule of carbon dioxide, CO2. Because of the double bonds, it forms it into a straight line so that they're all lined up, okay? So that is a linear structure. The third common structure is that of what is known as trigonal planar. Trigonal planar. Now, it's trigonal because it forms basically a triangle. But it's also planar because it's all in one plane. The atoms are all in the same plane as the central atom. So it is a trigonal planar, like this example of BF3. Here the angles are 120 degrees. Now the next one is called a tetrahedral. Tetra for four. So it has four equal triangular faces. Now this is actually what a methane looks like, okay, at least as far as the angles. Since it is in three dimensions, you see that each of these guys are as far apart from each other as they can get, all right? And it has four triangular sides if you were to connect between the hydrogens and so forth, okay? And the last one, called a trigonal pyramidal. Now, at first glance, it looks a little bit like the trigonal planar, but instead of them being all in the same plane, you can see how the central guy, the central atom, is raised up from the other three. So it forms a pyramid, hence trigonal pyramid. Ammonia is a good example of that. And here you see some pictures of that. Now, how do we know and how do we go from the Lewis structure where we can see that, where everything is flat, how do we go from that to this? All right. What can we use to explain the shapes that we see? Because this is the shape that is seen. They can actually figure out the angles and they know for sure that this is the shape. But why does it form this shape? That's where the VSEPR model or VSEPR theory comes from. Now, VSEPR, VSEPR, stands for the valence shell electron pair repulsion theory. And this is a model, same thing as a theory, This is a model used to predict the general shapes of molecules based on the repulsion between both bonding and non-bonding electron clouds. Now, as you guys know, valence electron pairs, whether they're shared as in a bond or unshared in a lone pair, they occupy specific orbitals which form electron clouds around the outside of the atom. Imagine, if you will, if that's an atom, these three-dimensional objects, these orbitals, kind of act or look like maybe flower lobes or flower petals that come off of it. And inside you would have a pair of electrons. Now these electrons, if they are shared, they might form a bond with another atom that has its own pairs. All right, and then these two would be shared. But still, you got to imagine that they branch off from the central part of the atom. All right, whether they're shared or unshared, they still are in these orbitals. But these electron clouds, being filled with negative electrons, are negative themselves. All right, so this cloud being filled with electrons is negative. This one's negative. This one's negative. They're all negative. And since they're all the same charges, they try to repel each other and therefore move as far apart as possible. All right? They don't like each other, so they will spread out as far apart as possible. But they're still attached to the central atom, which means they can't spread all that far. Now, if you only had two of them, all right, if you only had two of them, they would spread out in 180 degrees, wouldn't they? Imagine like these, all right, if these were the electron clouds, they would spread out as far apart as they could from each other. If they try to go closer, they start repelling each other. All right, but what if you had a third one? If you had a third lobe, these would push and repel those other two lobes, so that instead of being in a straight line, an additional lobe would repel it until they are as far apart as they can, thus forming 120 degrees. Well, what if you had a fourth lobe? What does that fourth lobe do? Well, that fourth lobe would be in the third dimension up here, and it would push those other lobes down. Okay, it's kind of hard to show here. It would push them down like this. Imagine on this model that there is another pair of electrons up here. You can't see them because the models only show bonds and the atoms are bonded to, not the unshared pairs. But imagine that sticking up out of there in a ammonia, there's an unshared pair of electrons. These guys would push these other three down into a pyramid type shape. So that if you had ammonia, and you know ammonia NH3 looks like that, you have the three bonds here, but you have this unshared pair of electrons that push it down into a specific shape. So that's VSEPR. VSEPR basically is a way of looking at a Lewis structure and realizing that, hey, I have both unshared pairs and shared pairs that will repel each other, thus forming the correct shape. Now, since Lewis structures show all of those valence electrons, they can be used to help predict the shape of a molecule. First step, draw the Lewis structure for the molecule. Voila. Okay? Then count the number of atoms bonded to the central atoms. All right? This represents the number of shared electron groups around the central atom. So in this case, we would have 1, 2, 3 bonds or bond groups attached to the central atom. If you had something like carbon dioxide, where you would have something that looks like that, double bonds still count as a single bond group. Since we're counting the atoms, there are only 2 attached to the central atom. In ammonia, there's 3. And then you go and you count the number of lone pairs of electrons on the central atom. Just the central atom. If any of these guys had electrons out here, you ignore those. It's only the central atom that matters. So this would have a single pair of unshared electrons attached to the nitrogen. Then you refer to the following table. The first column, if you notice here, says the atoms bonded to the central atom. So 2, 3, or 4 are the possibilities. Here, we have unshared or lone pairs of electrons around the central atom. So in our instance here, we have 3 shared and 1 unshared. So I go down to 3 shared and 1 unshared, and that tells me, actually, let's do this. All right, so we have 3 shared and 1 unshared. So that tells me that I have a trigonal pyramidal shape, which is what we already know is the shape of ammonia. Now let's try some other examples. Let's try BeCl2, okay? Now beryllium is in column 2, so it has 2 valence electrons, all right? And then there are 2 Cl's. Each Cl has 7 valence electrons, and they can each form 1 bond. So there's a bond there, and there's a bond there. Now when I count, I see that around beryllium, there are 2 electron groups and no unshared pairs. So when I go back, look here, it looks like 2 and 0 would mean that that is linear. All right, and that is in fact linear. BF3, we just did for BF3, let's do that one now. And by the way, notice here, I did not count these electrons as around the middle atom. Now boron, is in column 13. So boron has 1, 2, 3 dots. Each fluorine has 7, and each one can make 1 bond. So when I draw it, I have this. Now again, I count. I got 1, 2, 3 bond groups and 0 unshared pairs. All right. So that, if we go back, we see that 3 and 0 would be trigonal planar. And so it is. That's what this guy would look like. Okay, there's no electrons on the top and bottom pushing him into a pyramid shape, so it's a planar shape. Okay. Another example, NH3, I've already showed you that. That's 3 atoms and 1 lone pair. That's trigonal pyramidal. CH4, we go back and look at our original example. We have, once again, CH4. If you notice, that has 4 groups, 1, 2, 3, 4, and no unshared pairs around the central atom. So that would mean a tetrahedral. 4 and 0 is tetrahedral. And the last one is going to be water. Now water, H2O, has an oxygen, all right, that is bonded to 2 hydrogens. Now when you draw it, water looks like this. Now here you have 2 shared pairs of electrons, and you have 2 unshared pairs. So if we go back and we look at the chart, 2 and 2, it's right down here, that's bent. All right, that's a bent shape, 2 and 2. So we look at, for water, that is in fact a bent shape. And if you think about it, that makes sense. There are 2 unshared pairs of electrons that repel these bonded atoms downward and thus forming the bent shape. It's not tetrahedral because you don't see those unshared pairs. You only, quote unquote, see the bonded groups. And that is how you use Lewis structures to determine molecular shape.